Hello everyone, very good evening. Once again, welcome back to the session. Welcome to 360 TMG and interview preparation session here. Let's start for the day. So let's look into a few deep learning questions here. So what is this deep learning all about? We have deep learning concepts, right, which is a subset, and ultimately the whatever we are working here for deep learning is to give a AI driven product, build a AI driven product, right? So what exactly it is? It involves taking, maybe we can say, a large amount of structured data, or it is unstructured data, and we can use very complex algorithms to train your neural networks, right? So it performs complex operations to extract hidden patterns, we can say hidden features, even to a certain extent that distinguish between a cat and a rat, right? How can image of a cat from that of a dog can be explained? You can distinguish. So it learns very complex patterns also. That's where it stands high. That's where, though it's very subset of our data science and for machine learning, it is very, very powerful algorithms are associated with deep learning. So one of that algorithms here, we have big list, but the first one is neural network. So neural, the word neural, it's nothing but something what we have studied, right, about neurons. It is nothing but replicating the way humans learn, inspired by how the neurons in our brains fire. Only much simpler things here, where it consists of all the inputs to the cell body. We have all the inputs to the cell body and pushing the output. So a neuron, you call them as dendrites, you call them as cell body, you call this as axon, which gives us the output, right? So replicating the same setup, we have the inputs. These are nothing but your features. All are integrated, right? Summation is done. You will have an activation function which will give us the result. So it consists of 3 layers actually, but this is a setup where we have inputs followed by cell body and the output. So whatever we are talking, human brain, which will replicate this network, the neuron setup, right? So each and every part or every particular section what we are drawing, the same way how your neuron would work, right? So this setup, you call it as a perceptron algorithm. This works the best for your linear separation or few things where there is no complex patterns to be learned. It is a setup which is called as perceptron algorithm. It's a linear separable effective working functionality can happen here. So this particular neurons, what you are calling, they are nothing but the nodes. So these neural network, the same concept of neural network, it is used in CNN, or it is used in RNN, or it is used in GAN, right? expanding this topic of perceptron, which is not, there are two solutions if you have non-complex or non-linear patterns. Suppose I want to do a classification model only. Assume that I am working for a classification model, right? And I have non-linear data here. So this is linearly separable. But what if I have like this? Right? This is a complex. So people, when all the inputs are connected to this, then the cell body is having an integration function and an activation function. People tried with the different summation functions. They tried with different summation functions, right? Instead of sigma, they tried with a quadratic, they tried with a polynomial. But this was not correct solution. So they have come up with, instead of changing this, putting the summation function as is, they moved forward and they have thought of a new architecture totally, which is MLP, which is nothing but your multi-layer perceptron. It is nothing but multi-layer perceptron. So MLP is, instead of input and output, which you are not touching, in between the concept of hidden layers arrived. The concept of hidden layers, output, input, in between you have the hidden layers. It is the same structure of your perceptron algorithm, but additional to that perceptron, you have the hidden layers here. A single layer perceptron can only classify for linear separable classes with binary output, but MLP can classify non-linear classes also. So except for the input layer, each node in the other layers, you can also use linear activation functions and non-linear activation functions. You can use both. Now you are using non-linear activation functions because of the complex parameters. So input layers where the data is coming in, activation function which is based on all your inputs and the weights, giving us the output. So this multi-layer perceptron uses a concept called as back propagation concept, right? Which is a supervised learning method called as back propagation, where the network would calculate error, right? With this error, it will go back and it will try to do some changes to the weights. So it will adjust the weights in such a way that it will try to decrease your error. Okay, try to decrease your error. So actually what it is happening, for regression, you are trying to get the best fit line. In regression, you are trying to get the best fit line. The equation here is y is equal to beta naught, beta 1, x1. Here also you are behind a boundary, a linear separable boundary. Right? The same equation here, we are writing bias plus w1 x1. However, you call it here beta 1 as parameters. You are calling them as estimates. You are calling them as coefficients. Here this w1, you are calling them as weights. Same equation here also, this is replaced by this, beta 1 is replaced by w1. This is the best fit line equation. This is a linear separable classification. Right? Now, what is the role of activation function here? Right? So we even see that we have seen the expression for MLP. Then comes the role of activation functions. At the most basic level, an activation function decides whether a neuron should fire or not. It should be fired or not. Right? There are a bunch of activation functions here for us, like you have step function, identity function, sigmoid function, right? You have ReLU, ELU, leaky ReLU, right? TANH, softmax. These are the examples of your activation function. So this will decide whether it should spill out the result or not. It should spill out the results or not. It is decided by this. So an activation function will help us to get the result, to fire out the results. So when we are talking about such a scenario here, these activation functions are changing depending upon your different business problems. It cannot be same. Right? When you are using a multi-class, or when you are using a numeric prediction, or when you are using a binary, so your activation functions, your loss functions are changing accordingly. So that is where we use different activation functions. Right? So it is a thing that you get the output node. It is also called as a transfer function. Right? So it is to determine whether the results are 0 or 1, or it is numeric. If it is numeric, it's okay, it gives you a number. Right? If it is not numeric, it gives you 1 or 0. So the first activation function we can talk is identity activation function. It is nothing but a linear line like this. It can start from -infinity to infinity. Right? The output of the function, it is not confined any range. So you can use an identity function for y being numeric when you're working for y being numeric scenario. It's just a line, it's a linear line. It's nothing but you can say that f of x is equal to x, whatever you get. So, but it does not help for complexity patterns. It cannot work well for that. So this is nothing but linear activation function. In nonlinear activation functions, these are mostly used when there is a nonlinear pattern data. It makes it easy for the model to generalize or adopt any type of data, variety of data. So the main terminologies needed here is derivative or differential. So change in y-axis with respect to x-axis. It is known as slope. It is known as slope. So monotonic function. It is nothing but which entirely it is non-increasing or non-decreasing. So these non-linear activation functions, these are divided based on their ranges. Okay, based on the ranges, these are divided. Let us understand at least few here. Sigmoid. What is the role of sigmoid activation function? It's simple, like we have seen in logistic regression. It's an S-curve, sigmoid curve, right? So this range is from 0 to 1. So this is used for models where you have to predict. You want to predict probability. You want probability as output. You use sigmoid activation function. So the range of this is 0 to 1. Sigmoid is the right choice. And this function is differentiable also. The slope of the sigmoid curve at any 2 points, you can find it out. Right? So this is used, and extension of this is softmax. It is more generalized. It is used for multi-class problem. When you have a multi-class problem to solve, you use softmax activation function because it gives probabilities as output for more than 2 classes. more than 2 classes. So tan h is one activation function where it is much better than sigmoid curve. So tan h, sigmoid curve is 0 to 1. Tan h is -1 to 1. The range. It is also S shape only. It is also S shape only. But the advantage of tan h is that when you can expect negative inputs, it will be strongly mapping as negative only. Right? They don't map to 0, they map to this. This is also differentiable. And the very famous ReLU, this is used in CNN network, right? Convolution neural network. Why? Because its range is, it's a half rectified. The name itself you can see. Half rectified, and it cannot take any value between less than 0. Its range is 0 to infinity. So when you work with pixel values, it will never become 0. Pixel values can never be negative, right? So you take ReLU for CNN. The issue with ReLU is that it will not work with negative values, not for image data. Any other data, if you want to work, it will not work properly because 0 values cannot be mapped, right? It cannot be mapped. So because of that reason, you cannot do this. So any negative input, if you are giving to ReLU activation functions, it turns a value to 0 immediately in the graph. So which will affect mapping the negative values. For that reason, people have come up to solve the problem of ReLU into leaky ReLU. Right? ReLU is something like this, no? 0 to infinity. Leaky ReLU is little bit like this. This is the axis. You can see the leak here. This is the leak. Right? It helps to even find out the negative values, means below the axis. So the leaky range will be -infinity to infinity here. So like this, you have n number of activation functions here to study. Okay. There's a new term here now. What is loss function? What is activation function? What is the difference here? What is cost function? Till regression models, till machine learning algorithms, we say cost function, loss function, and error function, all are same. Right? There is no difference there, whether it is this or that. Right? So it is a measure to evaluate how good your model's performance is. It is nothing but when you have a setup, you have the cell body, integration, activation function, connection. This is there. This is your Y bar. So inputs, I'm just writing a perceptron algorithm here. So this is double comparison operator used to calculate the error. So this error, if you are calculating for each data point, you call it as loss function. So if you have 10 data points, this is my data set. 10 data points are there. You will get 10 loss functions. Average of these 10 loss functions is equal to cost function. So now, from now, we cannot say in deep learning what is loss function, what is cost function. We push that error, this cost function, what you got backward through this network during different training functions. And you just pull it back based on this cost function only. So whether it is cost function or loss function, choice is ours. Which optimization technique you want to use, it is ours to go back and do it. Right? So that is what you have to understand by back propagation. Most frequently used question or the word is back propagation. So what you can say, it's a technique where we are trying to improve the performance of the network, trying to update the weights and reducing the error. You're trying to update the weights. So it is which technique it is using? Back propagation technique. Why? To decrease your cost function, to improve your performance of the network, right? To reduce your error. That's where back propagation is used. There is one more concept here which is called as gradient descent. What is gradient descent? What is gradient descent? The gradient descent algorithm. How does it work in machine learning? One of the most used machine learning algorithms, right? You are playing a game where the players are at the top of the mountain and they are asked to reach to the lowest point here. If at all they are blindfolded, they have to reach to the lowest point of the mountain. What is the approach you think that person would make to reach to this point? What is the path he follows? He follows like this. Which path he follows to reach to this bottom? He will jump here and come down. He'll roll down and come down. The best way is to observe the ground and find where the land descends. From that position, take a step in the descending direction, iterate this process until we reach the lowest point. Suppose like this. Some path it has to take. So the first thing is it is an iterative optimization algorithm. It's an iterative optimization algorithm for finding your local minima of a function. To find the local minima of a function, we are using gradient descent. We are taking steps proportional to the negative of the gradient, means moving away from the gradient of the function from the current point. If we take steps proportional to the positive of the gradient, we are moving towards the gradient, right? So we are not focusing on how the jumps are happening. Our aim is it should reach to this local minima point. So it's simply like this. This is a gradient, rate of change. This is nothing but incremental steps. This reaching. So to minimize a given function, say the cost function, compute the slope, compute the gradient. Gradient or slope or derivative all mean the same. Take the first order derivative of the function at that point. Make a step, move in the direction opposite to the gradient. Opposite direction of the slope will increase from the current point by alpha times. Right? So that is what your choice is. So if at all you give a this all things will happen only for your sake of coming to the local minima point, means reducing the loss function. And it's least bothered that how many paths you take. It depends all on your eta. which is nothing but your learning rate. If you give a very, very huge learning rate, what happens? The jumps are higher. The jumps are higher like this. Jump 1, jump 2. If you give very low learning rate, turtle steps, right? It will take long time to compute. So it should be a minima, right? And this is taken like this, based on the loss function, right? How you give the learning rate, how fast your model is learning. Now it's an art of giving your learning rate. So gradient decreases while moving towards the local minima. The size of the step decreases. Learning rate can be constant over the optimization, and it need not be, iteratively varied. You need not vary it, right? It's all just imaginative that how well, if a ball is kept here, it's coming down. So gradient descent algorithm is also used in neural networks to optimize the loss. Backpropagation is used to update the weights. It's to update the weights. These are two used in the neural network. Cost function, based on the cost function, going there and updating your weights. Okay. Now, there is something called as tuning the parameters. Okay. What is this hyperparameters? Very, very, the real sense comes of this in decision trees and deep learning algorithms, right? We have a bunch of hyperparameters. What are hyperparameters? Hyperparameters are the weapons what we have in our hand to improve the performance of your model. Right? There's a difference between parameters and hyperparameters. When we talk about parameters, we are not touching. Like just now we have seen a regression equation. You're calling this beta naught, beta 1 values. Beta naught, beta 1 values as coefficients or parameters. But how these hyperparameters are different? So once the data is formatted correctly, it's a parameter whose value is set even before your learning process is started. So you are deciding from your end how the training is happening, right? Number of hidden units, number of what should be the learning rate, what should be the optimizer, all these things what you can do from your end, the changes in the design, the changes when you are compiling, the changes when you are fitting. When you are designing, when you are compiling, and when you are fitting. Right? Just like that now, just now we have seen if at all you are setting your learning rate very, very low, training of the model will progress like this. Right? We are making very, very small update on the weights. Before reaching to the minimum point, it's high, it takes a lot of time here. Right? But if at all it is ulta scenario now, if you give a huge learning rate, this is a hyperparameter, what you can change in the design when you are designing your model, right? It will jump so high that there is a chance of reaching this convergence point, but it will miss it. It will diverge. Okay? Model can give you good output. It could, if there are converged, it would have given good output, but it is diverging. It is missing this critical point here, minimum point. That's where it is an art of choosing the parameters. It is a time-taking thing to tune the right set of parameters. There is something called as data normalization. What do you understand by that? What is data normalization and why do we need it? What is data normalization? Why do we need it? So as we have the process of standardization or normalization, right? The process of this is the same data normalization, right? It is a pre-processing step where we try to eliminate any redundancies there in the data, right? Anytime you get data, the data is in different formats, right? And though that different format data, you cannot use them. Just like that, you cannot pass to the algorithm like that. So you have to rescale the values to fit into a particular range. It's very, very important here because to achieve a better convergence here, to achieve a better convergence, it is very, very important to do this. Sometimes it is a mandatory thing. What we do, right? It is a mandatory thing to do here. Okay. So when we are talking about the tuning the hyperparameters, doing normalization, all this, they take a lot of time for us, right? So it's a pre-processing step. What you have to do to rescale, well, it's most important thing when you are working with image data also, not only normal numeric data, for image data also, it's very, very important. Right? Okay. What is dropout? What is batch normalization? What is dropout? What is batch normalization? Dropout and batch normalization. Why it is required actually? Dropout, why it is required? Why batch normalization is required? Do you think it's really important for us to go for this? So dropout is something we definitely require. To converge. Everything is to converge, everything to reduce the problem of overfitting. And we require dropout is also one of the technique where we can use. You are dropping out few hidden units of the network randomly here to prevent maybe 20% of the nodes should be dropped out. So if at all I have a network like this, 1, 2, 3, 4, 5, first layer, second layer, 1, 2, 3. Hidden layers are there like this. Okay, this is a connectivity. You are not making it a dense network here. You have the connectivity. You miss few nodes, few neurons here, ignoring units using your training phase, saying that 20%, dropping 20% of the neurons connectivity. It doubles the number of iterations needed to converge. Right? To converge. So you are not this connection is missed. You're dropping out. If at all you have one neuron in the next layer, You connect to this dense network, but you leave the rest of the 3 neurons. We randomly drop out set of nodes at each training step. Right? The network becomes like very, very fast. So I miss this too. There is no connection required now. I'll drop these two. No connection is there. Right? Like this. 1, 2. This is there. Okay, I missed these two again. Connection. These are dropped out. But what is batch normalization then? So to reduce overfitting problem, dropout is required for us. To reduce overfitting, dropout is required. But what is batch normalization? Why is batch normalization important? What is that actually? So this is where this is helping for overfitting. This is helping us to improve the performance and stability of your network. How you are doing the story is here normalizing, right? So normalizing the inputs in every layer so that they have a mean output activation of 0 and they have a standard deviation of 1. So to improve the performance and stability here. That's where we have to do this, because this will help us to converge quickly to reach to the local minimum point, and your algorithm will learn the patterns. It will give you results easily. Okay. So next, there are few optimizers here, right? There are few optimizers here. So let us understand the difference between at least 2 or 3. Okay. So batch gradient descent and stochastic gradient descent. What is the difference between batch gradient stochastic gradient optimizers? So go back, update the weights back propagation to minimize the loss. To make your algorithm learn better, you are using different optimizers: Adam optimizer, RMS crop optimizers, stochastic gradient, mini batch gradient. Right? These are the different optimizers we can choose. Right? So what happens in batch gradient descent? See here, if at all you are having 1000 data points, you are passing this 1000 data points through this network once. All these are passed to this network once. It is called as one epoch. You are getting y hat, you are comparing with y, you are coming back, you are updating weights. Right? Each time you update weights, it is called as one iteration. It is called as one iteration. So in batch gradient descent, okay, one epoch is equal to one iteration. It means that all the 1000 data points, you will get 1000 loss functions. Taking these 1000 loss functions, you calculate the average, you get the cost function. Based on this cost function, it is going back and updating the weights. Right? So it will take one iteration here. If you are running for 15 epochs, 15 times it will update the weights based on the cost function. Based on the cost function. Right? That happens in batch gradient. So you are not bothered about other things. You are only focusing on not individual loss, total loss, average of all the loss, which is cost function. Based on this, you are calculating and updating the weights. The second one is stochastic, right? What is happening in stochastic? You have 1 to 1000 data points. It will take randomly. Stochastic means randomness. It will take one data point at a time. Randomly, it will take one data point, maybe 99. It will go, pass through the network, get the output, get the y hat for 99, compare it with 99, get the loss function, go back, update the weights. It will go back and update the weights. Again, take 98 or 998. Randomly, it will pass to the network, calculate the loss, go back and update the weights. So how many times it is updating? One time updation of weights is one iteration. One update of weights is equal to one iteration. For each of this data point, it is updating weights. So 1000 updates are happening here based on loss function, which is equal to 1000 iterations. If you have 1 lakh data points, 1 lakh iterations. N data points, N iterations it will take to update the weights. So it is taking time, right? You are giving better and better training, trying to reduce the overall loss. It is stochastic gradient optimizer. So both you can try, you can give it a try. It takes time to converge because if at all the volume of the data is high, batch gradient takes a lot of time. Batch gradient takes so much of time because it has to wait updates. It will go very, very slow. Right? So this is updating the weights more frequently. It is working with randomness. Right? It is totally again different. Right? How are these weights initialized in a network? How this initialization of weights happens? Either you can leave it to algorithm to assign them randomly, or you have to set up, initialize all the weights, start from 0. This makes your, if you set up weights, initial weights to 0, this makes your model simply linear. It's a linear model, simpler linear model, I can say. Just like a linear model. All the neurons, every layer will do same operation, giving the same output. What will happen? Your deep network will become useless, worthless. What is that? You are giving instructions. It is very, very high giving high performance giving model, right? So good thing here is leave it randomly. Initial weights, all the weights have to be initialized randomly. The weights are assigned randomly, initializing them very, very close to 0, but not to 0. It gives you better accuracy to the model. Since every neuron in the network, how many hidden layers you want, right? They perform different computations. And this is what we prefer the most. This is wrong way of dealing with it. Right? So different hyperparameters, different things. There is one more optimizer here for updating your weights, which is mini batch gradient descent. You can put it here only. This is mini batch, SGD. What it is more efficient when you compare to this SGD, more efficient. So the generalization here, it will be done using flat minima. It will allow to approximate the gradient to the entire training set. It will help us to reach out to local minima very, very quickly. right? So it will divide 1 to 1000 data points are there. It will divide it into batches. You can give batch size is equal to 100 or batch is equal to number of batches is equal to 10. So 1 to 100, 101 to 200, 201 to 300, 301 to 400. Like that, batch 1, batch 2, batch 3, batch 4, like that 10 batches will come. For every batch, you update the weight. Every batch, you update the weight. Every batch, update the weights. So it will take randomly, stochastic only, no, this also. It will take randomly one data point, loss function. One data point randomly loss. After all are passed through the network, calculate the cost function. Based on that, go back and update the weights. So here, one iteration is equal to one epoch here is equal to number of batches. 10 batches are there, 10 iterations you take. 10 times you update the weights. Right? That many iterations it will take. So, for example, now when you are training a neural network, when you are training a network, our neural network, sometimes loss does not decrease in first few epochs. Why is that so? Loss does not decrease. It will not come down in few starting epochs. What could be the reason? For this? Two reasons, major reasons are there for this. Yeah. So maybe you have given a very, very low learning rate. You might have given a very low learning rate. Or you have given a different regularization parameters very, very high, or because of this, they have stuck at local minima point only. You have to regularize it properly, make it high so that they don't stuck at that one point where you want, they are not coming down, but they are sticking it somewhere else. Right? So you might have got the difference now. What is an epoch? What is a batch? What is an iteration in deep learning? What is a cost function? What is a loss function? So when we are talking about epoch is something where one iteration over the entire data set. Batch refers to we cannot pass the entire data set to the network at once. So we are dividing them into batches, 1 to 100, 101 to this thing. If at all we have 10,000 images as data and we divide the batch size of 200, then epoch will run for 50 iterations. That is iteration. Right? Epoch, batch, and iteration. Okay. So what are the very, very famous libraries for us for this? To work with our neural network, go ahead with neural network. What is the one famous library here? Tensorflow, right? Tensorflow TensorFlow. So it's most preferred library. Why it is most preferred TensorFlow? TensorFlow, why? It provides you both C++ and Python APIs. It is very, very easy to work on, and it has a faster compilation time, right? When you compare it with your Keras and Torch. So the good thing about TensorFlow is that it supports both your CPU and GPU computing devices, right? Actually, what is a tensor actually? Tensor is nothing but a mathematical object. Okay, it is nothing but a mathematical object where you are representing it as an array of higher dimensions. So different dimensions and ranks, you can feed it as a neural network for sensors, right? Like if at all it is a 3D sensor, right? If you have a data like this, you call it as 1, 2, 3, 4, 5. 1, 2, 3, 4. So you can call it as tensor of such dimension. Right? 3D sensor means you have height, width, and depth. Right? For image data. For image data. So when we are talking about deep learning libraries, right? TensorFlow is a low-level programming language. Keras is a high-level programming language. So if at all you have to download or you have to install, you can do either Keras or you can do either TensorFlow. Okay, it's up to us how you can start off. So this is about the basic questions related to deep learning algorithm. So you can elaborate more. Right? And so thank you all for joining in. We'll connect next week, same time. Thank you.